Now, the second derivative is simply the derivative of the derivative. So y double prime of x here is one way of writing that, and that's the same thing as d2y by dx squared, and what we mean by that is d by dx of dy by dx. This is the rate of change of the derivative, this being the derivative, or the slope of the curve. So if we look at this curve here, which is a parabola I've drawn for us, and think about a distance delta x, then we can think about this slope here, which would be dy by dx at minus delta x over 2, and this one, which would be dy by dx at plus delta x over 2. And the slope at minus delta x over 2 for small delta x would be y of 0 minus y of minus delta x. So we're going from here to here. We could draw a line here as an approximation to that slope. So those two y's divided by delta x. And, of course, as we made delta x smaller, this would become a better and better approximation. And similarly, at delta x over 2, which is out here, dy by dx, the slope of this curve here, this straight line, and tangent to the curve, is approximately y of delta x minus y of 0 divided by delta x. Approximately so, as we said, as delta x becomes rather small. So, the second derivative, d2y by dx squared, which as we said is just the rate of change of the derivative, is the limit, of course, as delta x goes to 0 of dy by dx at delta x over 2 minus dy by dx at minus delta x over 2 divided by delta x. So we'll be able to use these approximations, which become valid as delta x gets small, and hence we can write the following. This is my dy by dx at this point, and this is my dy by dx at this point, at least approximately so, and in the limit as delta x becomes small. So, putting those all together then, d2y by dx squared is the limit as delta x goes to 0 of y of delta x, that's this one, plus y of minus delta x, that's that one, minus 2 times y of 0 in this case. And here we've just illustrated the second derivative round about 0 for simplicity, but we can take this round about any point. And this whole top line here has to be divided by delta x squared. So this is our formula for d2y by dx squared, or the second derivative of y, in this case evaluated at 0, but we could evaluate it at any other point. For the sign of the second derivative, we have going from a positive first derivative to a negative first derivative gives a negative second derivative, because we've gone from positive to negative, and that means that the derivative has decreased, and hence d2y by dx squared must be negative. The second derivative must be negative. We've gone from a positive value to a negative value, and that's why it's negative. Going from a negative first derivative, this would be negative, to a positive one would give us a positive second derivative. This derivative minus that one would be a positive number. Now, this is true anywhere that the first derivative is decreasing with x, that we have a negative second derivative. So at this point, the first derivative is decreasing with x. It's going from a larger positive number to a smaller positive number. It's also true here on the top of this curve, and it's true here as we're going down this side. Again, we're going from a smaller negative gradient here to a larger negative gradient over here. When you see a curve like this, a kind of top of a dome, that means that d2y by dx squared, the second derivative, is less than 0. Any region where the first derivative is increasing with increasing x has a positive second derivative. So here, for example, we're going from a larger negative number to a smaller negative number in terms of the slope. So that means that d2y by dx squared, or the second derivative, is positive. Here we're going from a negative slope towards a positive slope. Again, that's the same thing. d2y by dx squared is greater than 0. And over here, again, we're going from a smaller positive gradient to a larger positive gradient. That means that d2y by dx squared is greater than 0. So a dip, or a hollow, has a positive second derivative. Points where the derivative is neither increasing nor decreasing, that is, where the second derivative is changing sign, correspond, of course, to 0 second derivative. And these points occur here. For example, we're going from a positive curvature, that's a dip, towards a dome or a peak, a bump sticking up. At this point here, the second derivative is 0. Also here, where we're going from a dome with a negative second derivative to a dip with a positive second derivative, then at this point here, approximately, this is another point at which the second derivative has to be 0. And these points are known as inflection points. Points where this is true as we're changing sign on the second derivative are called inflection points. The second derivative can really be thought as how curved the function is, or its curvature. So this situation here, as we said, this is a dip. This has a large positive curvature. It's going from a negative gradient to a positive gradient, and this is changing rather quickly here on this curve, so that's a large positive second derivative. This is a small positive second derivative, so we might call this a small positive curvature. The gradient is increasing here as we go through that, but not very fast. This would be a large negative curvature, a peak, with a relatively narrow width here. That would be a large curvature, a large negative curvature. And this would be a small negative curvature here. The gradient or the slope is not changing very fast as we go from left to right, but it is still decreasing from a positive value in this side towards a negative value in that side, for example. Now, the value of the curvature does not depend on the overall height of the function. So this curve has the same curvature as this curve and the same curvature as this curve.